Well, hello everyone. Today we are here to talk about physics and a very specific aspect of physics, forces. And by forces, I mean the ones that are governed by the Newton's laws of motion. So, as you all know, of course, the Newton's laws they govern specifically how objects change their state of rest or motion, and how forces are responsible for that. Mechanics in general is broken out into two broad halves: the kinematics and dynamics. Kinematics basically deals with the study of the motion and how the motion takes place, and the dynamics tries to deal with how can we justify that change, or trying to explain why those changes take place. So in dynamics, we can either assign the fact that the change in state of rest or motion is taking place to forces or energies. Now, in this video, I'm going to briefly talk about how forces act on a given system. Taking a specific example, as you can see, there is a situation here. I'm using a simulation from the FET Colorado website. As you can see, PHET is written on the top right corner, right below the cancellation and the maximize bars. So you can go online, search for FET Colorado physics simulations, and you'll have access to a host of these simulations that you can run on your laptops or any other mobile devices, as long as it's equipped with Java. All right, there are some HTML5 simulations as well, so they don't require a Java template to run. So you can use that, run them online. So coming back to the situation, of course, as we see, uh, the system over here consists of this crate which is resting on this icy ground, right? And there is an incline at the other end. Now I can get rid of this incline. So now it's just level ground, a level playing field, as you may, if you may. So this person standing there, I mean, there's this person here standing, ready to push the crate from one end to the other. Now, as you see over here, and if you recall Newton's laws, the first law states that an object continues to be in a state of rest or uniform motion on a straight line unless an external impressed force acts upon it. First half of the law itself states that the state of rest or motion will be perpetuated. It will remain to be, or it will remain in its state of rest or motion, whichever motion it was in, right? As long as there is status quo, which means there is no external force. Now here, the word external can be interpreted as an external resultant, right? A resultant force, a net force, because it's very hard, you know, to find systems or objects in our immediate surroundings where there are no forces acting at a given point in time, right? There are always, forces that are present, that are being exerted on a given system at any given point in time. At this point, as you sit on your chair and watch this video, your weight is pulling you towards the center of the earth. The chair is offering normal reaction to you, your weight. And the weight of the chair and you taken together is actually acting on the ground. And the ground is offering a reaction to both you and the chair. Right? Now, if you think about that situation and project it over here, we see the crate, right? The crate has two forces acting on it at this point in time. It's at rest, of course, there's no doubt about that. And we all have these rudimentary powers of observation which allow us to see that yes, there is the object is at rest. Along the vertical direction, Fg represents the weight of the crate acting downwards, and Fn represents the normal reaction offered to the crate by the ground. Now see, of course, you are aware, you push your hand against the wall pushes back, right? Exactly, that's the point. So in this case, the crate pushes down on the ground pushes back on the crate, which again is Newton's third law. To every action, there is an equal and opposite reaction. So the action over here can be thought of as the weight of the crate acting on the ground, and the reaction is the normal force acting on the crate because of the ground, as the ground's reaction to the weight of the crate acting upon it. So one very important takeaway from the third law that you must keep in mind, we will again discuss the third law in detail later on. One very important takeaway over here is that the action and reaction forces, they don't act on the same object. Now, if I were to tie a rope to this crate over here and have one person pull it this way and the other person pull it that way, and they are equal and opposite and they cancel each other out, they won't be action-reaction pairs because both the forces are acting on the crate. But in this case, the weight of the crate is acting on the ground and the normal contact or the normal reaction offered by the ground is acting on the crate. So it is very important for you to note that for an object or a pair of forces to be Newton's action-reaction pair or Newton's third law pair, the forces must act on different objects. Right? All right, coming back to Newton's first law again. So as we see over here, the forces, the normal reaction and the weight, they are balancing each other out. So this is a situation that we refer to in physics as equilibrium. Right? And equilibrium implies that the object remains where it was at rest, or the object continues to move with constant velocity. Now, if you imagine a car moving along the road at a constant velocity, at a constant speed, moving forward, right? It's not accelerating, it's not slowing down. Even that is equilibrium, right? Even that is equilibrium because there is no resultant force. Like over here, there is no net force, there's no resultant force, even though there are forces acting, which is what I was talking about. You will never find a system around you where there are no forces acting. If there is no force whatsoever, there will be these two forces acting on it. Now, the situation, the point of this video is to try and make you understand how a resultant force causes a change in the state of motion or rest of the system. So in this case, it will be a change in state of rest. Now, it's an icy slope. The reason I chose the icy slope is because it has no friction. So let's see what happens when this man pushes this. It's a constant force of 17.25 newtons. For some strange reason, I chose this. And he pushes it right through to the other end where the other wall is. And if I do the same, the box continues to move even after the force has been removed. So now what you see over here is basically the box moving in this direction, right? Under the effect of the initial force of 17.25 newtons. But because there is no resultant force anymore, because there's no friction, there's no applied force, and the vertical forces are balanced, it keeps moving at a constant speed. Right? So always remember that even an object moving at a constant speed slash velocity, like it's always better to refer to it as velocity. Speed, it's a little misleading. Speed is only just the magnitude, but velocity represents the magnitude and direction. And uniform motion is generally referred to with respect to uniform velocity or constant velocity. So when I say constant speed in terms of forces, please decode it as constant velocity. Might be a slip, I'm only too human, right? Okay, so coming back to that, therefore, the situation can only change when there is an external force. So we saw over here the external force was the applied force, right? Which is denoted by the F sum over here, right? The F sum is the sum of forces or the resultant force. As you see very well, the resultant force was acting towards the right, so the crate was moved towards the right. Perfect. And as soon as the force was removed, right, because of the initial direction of the motion while the force acted, even after the force was removed, because there were no other forces, it kept moving towards the right or towards the left, as we saw in the previous case. So once again, an external force keeps moving towards the left because the initial force was towards the left, and once the force was removed, there was no other force acting on the system that would change that. So now let's just change the angle of the ramp a little bit. So there we have it. The angle of the ramp is at 20 degrees. It was 30 degrees at first, but just change a little bit here. And slope is still icy. So now let us try and see the effect. Now from minus 10 to 0, it's still the same as previous. Now, as soon as you push it up the ramp, let's see what happens. Let's show the body diagram. Right. Now, as soon as we look at this, the angle of the ramp is 20 degrees and the crate resting on it at this point, it's resting because I have hit pause. It might not rest because there's no friction holding it back. Now the resultant force is in this direction. So if I play it again, that's how it goes. Just slides back down, which is something that we all have experienced, right? Like pushing something up the ramp and then looking at it slide back down. It's probably something that we've all encountered every now and then. Supermarket would push the, trolleys up the ramp or down the ramp, right? I mean, down the ramp is easier because it naturally slides downwards. But why does it slide downward like that, right? So that is another example of Newton's first law, in fact, but slightly different because the ground is not level anymore. So what we do over here is we push it up the ramp, right? And let's see. Pause it again. So the F sum, which is the resultant force, as I was saying before, is now acting down the ramp, which makes sense, which is why the object slides downward. So the natural resultant over here is always in the direction down the ramp. The other thing that has changed from the previous situation is that the normal contact is still perpendicular to the ground, but the weight is not. The reason being, the weight of an object always acts towards the center of the earth. And one must note, even though the position of the ramp, which was earlier level, has been changed, the position of the center of the earth has not changed. So it still acts vertically downwards. So if you look at the diagram over here, it shows you the x and the y. The y can be thought of as the vertical on the level ground, and x can be thought of as the horizontal on the level ground. Now, as you move along the ramp, the vertical and the horizontal, that sense, that changes. So the vertical would now be perpendicular to the ramp, and the horizontal would be along the ramp. Just think about x and y rotated in an anti-clockwise direction. towards by an angle of 20 degrees, right? So just like so x is over here now and the y is over here, the yellow arrow. So normal contact perpendicular to the surface and the weight acting vertically downwards. So this is where we need to consider resolution of forces. And which force do we resolve? Normal contact, the F sum, or this? Now always remember that resolution of forces, the choice to resolve a force, depends on your choice of x and y, or your choice of vertical and horizontal. Now here, my choice of vertical and horizontal would be vertical, perpendicular to the ramp, horizontal, along the ramp. Perfect. So therefore, we see that the vertical is actually denoted by Fn. So Fn is actually along the vertical direction, so there is no point in resolving it. F sum, the resultant, is parallel to the incline, which means it is along the incline, so there is no point resolving it either. But wait a minute, we have the weight. The weight is acting vertically downwards, and this vertical has actually no bearing on the horizontal or the vertical with respect to the ramp. So we resolve the weight. Now the resolution part will be shown in another video. We see as we resolve, there is a component along the ramp and there is a component perpendicular to the ramp, which is quite natural, right? When you resolve forces, you get a component along the vertical, or the horizontal, and along the vertical. So because it's pointing downwards, the vertical will be downwards and the horizontal would be in this direction, which makes sense. So F sum is nothing but the horizontal or the along the ramp component of the weight. So the resultant over here can be found by resolving vectors. So that's a physical situation where finding the resultant force is not very straightforward, and you need to apply your knowledge of resolution of vectors in order for you to be able to do it. Right? Now, how do you find the resultant force? Of course, that's the second law. Force equals to mass times acceleration. Absolutely. So now I change the surface to wood. You see what happened? If I change it to ice and I push it there, it doesn't stop, right? Because there's no friction to stop the motion. But if I make it into wood and then push it, well, it didn't even move. It moved, went up, and stopped. Stopped again. So over here, I would like to point out the horizontal equilibrium situation here as well. As you see, this person is pushing it with all his or her might. He is increasing, or she's increasing the push on the crate, but to no avail, because the FF over here represents the friction. Right? And as we see, the friction and the applied force, they are equal. Now, of course, Newton's first law again, if the forces are equal and opposite, right, there's equilibrium. One move, right? So FA and FF, they cancel each other out and therefore again produce equilibrium, and hence the object does not move. So I have to increase the force. Right, 494.5 roughly, it works. Now, in general, the force required for an object to move, overcoming its friction, is given by a formula, mu s times mg, where m is the mass and g is the acceleration due to gravity. Now, mu s is given over here, 0.5. M is given as 100 and G is 9.8. Do the math. It roughly comes to somewhere between 495 to 500. And that's where it started moving, 494.5. Right? So, in the real world, where friction is not negligible in most cases, even for ice there is friction, but in the simulation they've chosen ice to represent a situation where friction is almost negligible. All right? A smooth surface is a surface that is mostly devoid of friction, and we use it to simplify the situation. You might find problems where they tell you upfront that friction has to be neglected, and that is solely because you have to look away from the fact that friction might play a role. But in certain cases, they would say that it's a rough surface. A rough surface implies that you cannot neglect the presence of friction. Okay, so over here, as we see that the block is held in place over here. All right, the block is at rest. So, as we see over here, there is no F sum, which again brings us back to Newton's first law. If there is no resultant force, the object continues to be in a state of rest or uniform motion. So the object is held in place on the ramp for the lack of this F sum. Now what happens if I push it further? Starts moving, right? And we also saw the return of F sum, right? So we will discuss how the resolution of vectors takes place and how we can use vector resolution techniques to understand the components that I was talking about, parallel to the ramp and perpendicular to the ramp, and how that affects the motion, how that affects friction. Till then, take care.